Alright you guys, so in this video I'll be lecturing in chapter 4, section 1. So in this one we're gonna go into integrals. This section is going to be covered in exam 3, so we are technically done with the material for exam 2, which has all been uploaded to Blackboard already. Exam 2 is gonna cover both chapter 2 and chapter 3, so make sure you study all the sections on derivatives and their applications. Anyway, so in this one we're gonna look into antiderivatives, and what I mean by that is that whenever you guys normally take a derivative, you basically reduce the form of the function, so you differentiate it. Let's call f of x, for example, 3x squared, right? So if I were to differentiate this, it will say f prime of x equals what? 2 times the 3, that's 6x, correct? So differentiating or going in this direction is always explicit. It's very easy to find, and depending on the problem, you could have implicit differentiation, but even then the answer is going to be exact. But for antiderivatives, that's not always the case. But before we go into that, I just want to make one note. Usually, when you start with a function that is denoted f of x, if we're differentiating, you go to f prime of x. But if we're taking the antiderivative of whatever f of x is, you can't exactly make it f negative prime, right? You can't just undo this one when it's not even there. So the way to go would be to capitalize the letter. So whenever you see f capital of x, this is meant to denote that this function is the antiderivative of that function. Make sense? So I'm making it bigger, so to speak. So for example, if I'm going to use the exact same value over here and say that f of x is actually 3x squared, right? Then f capital of x is going to be the value that you had initially before you derived it to get to this value. So this essentially means that your f capital of x equals, f capital prime of x equals f of x. Make sense? So when you take the antiderivative of a function, you're basically saying that that function is the derivative of the one I'm trying to find. Make sense? So logically, you can technically backtrack and undo your steps. So for example, over here, knowing these two, if you start here and go, okay, I have a 6. I want to add a power here. Since this is the power of 1, that means it's going to go to the power of 2. And whatever this power here, because when you took the derivative, you multiplied it. So I'm going to divide whatever new power I have. So it's going to be 6 over 2 times x to the second power, making it 3x squared. Make sense? So in this case, if you want to do the exact same thing, you increase the power of x, making it 3, and then you divide the coefficient, which is 3, by that same new power, making it 3 over 3x to the third, which basically equals x to the third. And that makes sense. I mean, if you derive x to the third, you end up with 3x squared. But this seems like a tedious way to do it. So instead, we're going to show you guys integrals, and that's how we're going to solve most antiderivative values. So before I move on, I want to show you guys the definition of what an antiderivative really is. Let me go up a little, get this in line. Okay. So the definition of an antiderivative function is a function f, notice the capital letter, is an antiderivative of f, notice this one is small, on an interval I. Alright? So when f capital of x prime, right, equals f of x for all x in I. So for any x in I, when the f capital of x prime, so the derivative of that function equals f of x, that means that f capital without the prime is the antiderivative of f of x. Make sense? So that's basically the definition of an antiderivative. Now, note that we say an antiderivative and not the antiderivative, and there's a reason for that. It's because the answer is not always the same. We have an abstract or an arbitrary value we call c, which is meant to represent a constant. This value is always added to the result of any antiderivative function you find or any integral you solve. And there's a reason for that. Whenever you derive a normal function and that function includes a solitary number, once you take a derivative, that number disappears, right? The derivative of a constant is always 0, which means that if you start with a derivative and try to find the antiderivative, there is a chance that that constant was there, and when you derive the function, it disappeared. So when you undo what you did, you're not going to get it back. And let me show you an example of what I mean. I'll give you 3 examples of functions. Let's call this f1 of x, right? And this one equals x cubed. f2 of x, and this one equals x cubed minus 5. Let's do another one, f3 of x, and this one equals x cubed plus 97, right? So these 3 values. Now, if I want to find the derivative of each of these, let me give you a hint. It's going to be the exact same function. F of x, which is a derivative of f prime of x, right? So let's establish the relation. And f of x itself actually equals 3x squared, which is the one we just saw. Now, this value is the derivative of each one of these. That's true. If you derive this one, you get that one. If you derive this one, you get that one. And if you derive that one, you get the same derivative. But notice that this one has nothing aside from the x cubed. This one has a minus 5, and this one has a plus 97. So if I were to give you this initially and ask you to find the antiderivative, this is the one you're going to find. You can't predict what the numbers are going to be, or even if they're there. The only thing you can actually find is any value that includes x. So that's why whenever you find the antiderivative, it is customary to write it like this. So you write the answer you found, which is x cubed, and then you add plus c. Now c is an arbitrary number and it could be anything. So it could be 0, it could be negative 5, and it could be positive 97. Make sense? So that's why we present a constant c every time. And let me tell you this, every time people solve an integral or find an antiderivative, they easily forget to add the c, because the x is the part you solve for. The c is the part you need to remember. It's conceptual. You just need to remember that there could possibly be a number, and that's why you always write down plus c. As long as you're finding an antiderivative value or solving an indefinite integral, which are the same thing, then you need to write down plus c every time. Okay? Now, let me show you guys the verbiage for theorem 4.1 before we move on, because I want to make sure you have it in your notes. So let me do that real quick. Alright, so here we go. Theorem 4.1. Now, theorem says, if f capital, note the letter, is an antiderivative of f, on an interval I. Then g, which is supposed to denote a different function, and then we're going to establish what the relation is an antiderivative of f. So note, two different functions, both antiderivatives of f, okay, on I, on the same interval. And this is the case if and only if and only if g itself is of the form g of x equals f of x plus c for all x in I. C is a constant. So this theorem basically says what I just explained to you guys, where we saw three different functions. All of them have the exact same derivative, f of x, but they were somewhat different. F of x itself was just x cubed. Let's call the other two g of x. One was x cubed minus 5, and the other was x cubed plus 97. So I'm basically saying that a different function, aside from f of x itself, could possibly be an antiderivative of f if the form of g of x is the same as f of x plus a constant. It doesn't matter what the constant is, then that function could possibly be an antiderivative of f. Make sense? Which is why we always add c. Alright, so that was the idea of antiderivatives. Let me show you guys an example. Okay, so for example, the question says, find the general solution of the differential equation. Alright, now if you guys aren't familiar with the concept of a differential equation, maybe I should explain it to you real quick. So, let me see. Okay, because I think I have a definition in here somewhere. I like having the exact wording. But to explain it real quick, it's basically the family of functions represented by, let's call it g, in general antiderivatives, right, of a function f. So kind of like the theorem we just talked about, right? And let's say g itself, so g of x, equals x squared plus c, right? And let's say this is the general solution of, and here we have g prime of x equals 2x, right? So this is the derivative of that one. And this one is in the antiderivative form because I have the plus c in there, right? So this right here is considered to be a differential equation. So a differential equation, let me give you the definition real quick. Definition of diff eq. I'm not sure if you've heard that term before, but diff eq is a differential equation. So a differential equation, oops, yeah, that's right. Differential equation in x and y, right, is an equation that involves x, y, and a derivative of y. Right? So the idea here is that if if you have an equation that has a derivative of y, derivative of x, and has x and y in it, then that equation is basically considered a differential equation. Think implicit differentiation, how when you had a y inside the function, and how we had to first derive as if it were x, and then we had to derive it as if it were a function of x. So we wrote y prime in there. That's the same idea. We did that because y is considered a differential equation. So whenever you see, for instance, y prime equals 3x, so this is a function in terms of x, where x is derived, and this is a side where you only had y, and because it has nothing else, the derivative was 1, and you multiplied it times y prime. So this is considered a differential equation. Another example would be y prime equals x squared plus 1. That's another example of differential equations, right? Now this is a very broad explanation because you're going to go into the definitions of differential equation and how to solve them later on, especially in Calc 2. So I don't want to confuse you too much, but this is just a basic understanding to know how integrals work. But yeah. So now let's go back to our example. So the question says, find the general solution to the differential equation. So for all intents and purposes, whenever you hear the term differential equation, just know that it's an equation in terms of y and x, where you have a derivative of x, derivative of y, and different values, sometimes y, sometimes x, sometimes both. Alright, so anything that has derivatives in it, basically, that includes both x and y, and has a derivative of y included, then it's considered a differential equation like this. Okay? So, actually, I'm out of room, so let me just remove the page. Okay. Now, example says, find the general solution of a differential equation that they gave to you. dy dx equals 2. That's all. Okay? So, dy dx is basically a differentiation of y divided by differentiation of x, right? So this is a derivative of y in terms of x. This is the part we usually write in this form, y prime. Okay? So it does have y prime in it. So a solution of this, if you were to solve it, you'd go, okay, we have a 2. That means we derived it and only ended up with a 2. So this 2 was probably multiplied by an x, because if it was 2 alone, it would have disappeared, right? So it's basically multiplied times x to the 0 power, which is 1. Now, when you derive, you subtract 1 from the power. So when you find the antiderivative, you add 1 to the power. So this turns into y equals 2x to the first power. And you divide by the new power, but since it's 1, 2 over 1 is still 2. So this is your answer, right? Now, using 4.1, the theorem we just saw, right? So using the 4.1 theorem, we rewrite this in the form of 2x plus c, because there could have been a number there, but when you found the derivative, it disappeared. Make sense? So this is the final solution. Okay? So let me find a different example for you. Oh, actually, before we move on, I remembered one more thing I wanted to mention. On the concept of differential equations, you see how I wrote this like this, or derivative in terms of y. You see how dy dx is usually written, and when we first introduced derivatives, I told you that this equals the same thing as y prime, same thing as f of x prime, same thing as dx, right? Do you remember this form? And a bunch of others, right? So I want to show you a new way of writing it. It's kind of a segue into integration, so bear with me. Over here, whenever we write the general form for derivatives, we say dy dx, and then I'm just going to use the 2 because that's the example we have. And actually, let's just go with f of x, right? So dy dx of f of x. So this right here is a function. We are dividing dy by dx, differentiation of y in terms of differentiation of x, making y a function of x, right? So what if we multiply both sides by dx. I'm essentially canceling the denominator. So you end up with dy equals f of x dx. So what happened there? So it is convenient to write it in the equivalent form as dy equals f of x dx, which is the operation value you need, because whenever you're finding the integration, you are basically going to integrate a function in terms of dx to find whatever dy was. Because the reason, whenever we have a derivative, the reason we divide it by dx is because it's supposed to be considered a function of x, and when you find the derivative of it, you need to divide it by a differentiation of x. Make sense? So removing this basically leaves you with dy, which enables you to integrate both sides. So because this is a differential equation, over here I have nothing, so it's technically 1, right? So if you take the integral of both sides, over here you end up with y, and over here you end up with f of x, whatever it was supposed to be, plus c, therefore finding your antiderivative. Make sense? So this is why whenever you find a derivative, the function is always going to be multiplied by dx. So whenever you see this notation, this means integral, right? And we call them indefinite integrals. And the reason we do that is because it has no limitations. Later on, you will see this form where you have, for example, 1 to 5. This is a definite integral. This is basically telling you that this integral is integrating this function on the interval 1 through 5. So it specified the numbers. So for the first one over here, whenever you solve this, the answer is going to be in this form. It's going to be a function plus c. For this one, the answer is always going to be a number, because you're going to find a function, you're going to plug in these values, and find the actual solution for that interval. Make sense? But we will get to this one later on. Right now we're discussing that one. Just the indefinite one, the generic form. So let me give you an example and show you what it looks like a little. Okay, let me go up a little bit. There. Okay. So, for example, if I give you a integral of f prime, I'm gonna keep things a little abstract here, just to show you a few basic rules, and then we'll start applying them to actual functions. So bear with me. Ooh, maybe I can zoom in a little because it looks kind of small. There. Okay. So we have an integral of f prime of x, right? Dx, remember, you always multiply it times dx, equals fx plus c, right? So this is called the inverse. So the integration is the inverse of the differentiation. So when you do this, you're basically integrating. This is the basic form of any integral you're gonna see, right? So here's another idea. Technically, since an integral is the antiderivative of a function, so I guess it would make sense that if we took the derivative of the antiderivative, oops, it's supposed to be capital, right? So f capital prime of x dx, right? Equals, so over here you're taking the integral of f prime and you are differentiating it again, so that should lead you back to f prime, right? Because we took the integral, that means it took you to f without the prime, and then you took the derivative, so you go back to prime. Make sense? So taking a derivative of an integral cancels it out. Yeah? So now let me show you a few formulas that will help you guys. I believe these are actually in your book, but just in case they're not, I will write them down for you. Because your book is a new edition, and I'm not sure it has everything the old one I'm using has. So I wanted to make sure you have these. Okay, so let's give this a title. Call it Basic Integration Rules. Alright? So these are basic integration rules. There's probably going to be a lot more, but these are the easiest ones so far, and they like basic knowledge that you need to solve the initial integrals I'm going to show you. Alright? Okay, so I'm going to have two columns. We're going to call the first one differentiation formulas, and the other one integration formulas, because I want to show you the contrast between the two. So I'm going to just write a squiggly line over here, like this. Okay, so if you have d dx of c, it's going to equal 0, right? Whenever you take a derivative of a number, the answer is always 0. Okay? As for integrals, if you integrate 0 dx, the answer is going to be c. Which makes sense, because over here you're supposed to be undoing whatever this did, right? So, if it was 0, you take the derivative, it goes back to being c, right? Okay, so what about here? We have d dx of kx. So that equals k, right? If you have a number multiplied by x, x being to the first power, notice, right? So when you take a derivative, the x is going to disappear and end up with just a number. So over here, when you take the derivative of k, dx is going to equal k times x, what we started with. But because of theorem 4.1 and the fact that you're never sure if there was actually a number or not, you're always going to add plus c. Okay? So, kx plus c. So these are going to be kind of like your guidelines to find your antiderivatives quicker instead of trying to guess it out. Okay, so let's do one more. How about d dx of, now what are we finding derivative of? Okay, how about k times f of x, to keep it more abstract, right? So any function of x, so it's going to be just the number times the derivative of that function. That function derived and the number remains. Okay, now why is this helping me? I mean, it's technically kind of like this one. The reason I'm showing you this is because I want to show you a specific property, which is if you have a derivative of a number k multiplied times a function f of x, which is f prime in this case because I'm finding the integral, dx, right? This equals k on the outside times that integral. And I mean by that, you can take the constant out. If you multiply the constant that was inside the integral, outside of the integral, the answer is going to be the same. Make sense? So over here, f prime of x dx. So that didn't change. I just took out the number. Alright? So what I mean by that is, if you want to look at the previous example for instance, over here we have kx, derivative is k. Over here we only have k. Does that mean I can take it out? Yes, you can. If you do, you'd end up with a 1 because it's k times 1, right? So if you do that, take this out, then you end up with integral of 1, and when you do that, you end up with x. K was on the outside, and you multiply it times the x, therefore k times x. Make sense? Now, usually we don't take out the numbers outside the integral unless you're trying to simplify it because the function is too big. but otherwise it's an unnecessary step. The only purpose it has is to simplify what the function looks like to make it easier for you to solve. Alright? So that was a property that's very useful. So let me give you more about ddx of, bear with me, now we have f of x plus or minus g of x. Right? So this is where we use the rules, right? Over here, when you have functions added or subtracted, as far as when it comes to derivatives, it doesn't matter, right? You derive each of them separately. So this is supposed to equal f prime of x plus or minus g prime of x, right? So let's see what the integral would look like. So an integral of two functions added or subtracted from each other, both prime, right? dx equals separate integrals. Now again, you can technically solve it at once, but if it's too confusing, you can split the integral between both of them. So it becomes integral of f of x dx plus or minus integral of g prime of x dx. And notice when I split the integral, each got their own dx. Whenever you have an integral, accompanying dx must be there. Make sense? So, and now you can solve each separately, and the answer will be correct. Here's another thing. This one is going to be f of x plus c. That one's going to be g of x plus c. You can technically add the c's and just write 1 plus c. That's fine too. You don't need to worry about that because, again, c is an arbitrary number, so it doesn't matter. Okay? Let me give you one more. Hopefully this will make things easier on you. Okay, so dx. This is the one you guys are probably going to use the most until you get the hang of things, which is x to the n power, right? So any x to a specific power, this is where you learn how to deal with the powers. Okay, so when we're finding the derivative, we say you take the power, you multiply it in front, and then you subtract 1 from the power on top, right? That's a derivative. Now, what does the integral look like? Let's see. So, integrate. We have x to the n power. And notice, I wrote this one. It's because it will be a lot easier for you to see the pattern. If I write this one, it might be a little confusing. Now, it applies to this one. It applies to any x that has any power. I just want you to see what it looks like when there's no coefficient and there's no subtract 1. Just to see what it looks like. Yeah? So I'm doing that one. So, x to the n power. If you're finding the integral of x to the n power, it would equal the following. You with me? X to the n plus 1 power on top. Yeah? I mean, it makes sense. When you're finding the derivative, you subtract 1. When you're finding the integral, you're going to add 1. So, x to the n plus 1 instead of n minus 1. Yeah? Also, you are going to divide it by the new power. Make sense? So over here, I had n plus 1, which means the denominator is going to be n plus 1. Basically, it's going to be x to the n plus 1 times 1 over n plus 1, whatever the power is. And then you add plus c. Don't ever forget the plus c. And there's obviously a condition saying that n cannot be -1 for this one, otherwise the denominator would be 0. You just can never divide by 0. Okay? So, just to show it to you, I'm going to find the integral of this one, because so far we've been finding the integral of this one to show you that it matches that one. So I'm going to do that. But this is the rule that's a lot easier to remember, so I recommend getting familiar with this one instead of the next one. Well, let me do it real quick. So here we go. Integral of n times x to the n minus 1 dx, right? and it equals, following that rule, we say, okay, so we have, according to a rule we saw above, right here, the coefficient k gets carried out. So let's do that. Yeah, I'm taking the n out, so n times the integral of x n minus 1 times dx. Yeah, okay, so now n's still there, no problem. Now it's multiplied times this right here, which is x to the n minus 1 plus 1, right? It was this originally, and you're supposed to add 1 to it. So these two 1s are obviously gonna cancel, leaving you with x to the n, just x to the n. Yeah? Okay. So now that my new power is x to the n, that means that the denominator is also gonna be n, because it was originally n minus 1 plus 1, right? So these two are also gonna cancel. So over here we have an n, over here we have an n, they cancel, and the answer you get is x to the n, which is what we had. Make sense? But like you saw, this can be a little confusing, so I recommend studying that one instead. And last but not least, let's not forget the c. Okay? Alright. So these are the basic rules. I actually have a lot more, but I think I'm gonna do that in the next video, not to make this one too long. So I'm gonna stop this one and pick it up in the next one.